Section 7.5 Applications. We recall the Laplace transform for those common functions that we use all the time. Laplace of 1 is 1 over s. Laplace of t to the n is n factorial over s plus s to the n plus 1, and so on and so forth. We covered those back in section 7.1. Linearity of Laplace transform. If you have alpha and beta constants of f of t, g of t, two functions, then it's alpha Laplace of f plus beta Laplace of g. The same thing applies for the Laplace inverse, that the Laplace inverse linearity works as well in the inverse of Laplace. We recall the first translation theorem. We're going to use it somehow, somewhere. So we have the Laplace of e to the at f of t is f of s minus a, where capital F of s is the Laplace of small f of t. We have the Laplace of the nth derivative of f of t. We covered in the previous section. It's s to the n f of s minus s to the n minus 1 f of small f of 0 minus s to the n minus 2 f prime of 0 all the way down to the nth minus 1 derivative, where capital F of s, again, capital F of s is the Laplace of f of t. We also covered the Laplace of the convolution of f and g. It's the Laplace of f of t times the Laplace of g of t. We can also write it as capital F of s times capital G of s. So what are we going to be doing in this section? We're going to be using Laplace transform to solve differential equations, those linear differential equations with constant coefficients. So if we look at this nth derivative differential equation, a sub n dny dtn all the way down to a0y equals g of t, where the initial condition y of 0 is y sub 0, y prime of 0 equals y prime sub 0, all the way to y is 0 to the nth minus 1 is the n derivative, n minus 1 derivative of y sub 0. And what we have here, this is of 0, and what we have here is by linearity, if we take the Laplace of this linear differential equation, we get a sub n Laplace of the first term plus a sub n minus 1 Laplace of the next one, all the way to a sub 1 Laplace of dy dt plus a0 Laplace of y equals Laplace of g of t, which is on the right side. Now, going back, how do I find the Laplace of dn dtn? Well, we recalled it here. You see this part here. That's what we recalled, the Laplace of that. So here, if we apply it to this one here, we get Sn y of s. Y of s means capital F of s. So think about capital Y is capital F and small y is small f. So if you substitute that in, you're going to go all the way down to this y0 of n minus 2. And then we do the same for the next term, which is the nth minus 1 derivative. It goes all the way down the same way. But the first one starts Sn, this is Sn minus 1. And then the last term, a0 Laplace of small y. So again, Laplace of small y is capital Y of s, and the Laplace of small g of t is capital G of s, capital G of s. And then what am I going to do with this one? We're going to multiply all of these out and collect the terms that go with y of s. As you can see, there's y of s, and I factored all the terms out, grouped them. And then on the right side, we got all the terms in the other terms involving a sub n minus 1, all the way to g of s. And why do we do it this way? Because we want to solve for capital Y of s. Why do I have to solve for capital Y of s? Because as soon as you solve for capital Y of s, you can take its Laplace inverse Laplace, and get small y of t, because that's what I'm looking for. To solve the differential equation, we need to find y of t, small y of t. So we get y of s to equal the Laplace inverse, or the Laplace of y of t. So what do we do here? We solve for y of s by doing some algebraic manipulations, and then solve for y of t using the inverse Laplace of capital Y of s. And note something, based on the theorem that I recalled earlier, or for the derivatives, it's good to know these by heart. It saves a lot of time and going over it again and again. So the Laplace of y is capital Y of s, that's the easiest one. The Laplace of the first derivative is s capital Y of s minus y of 0, and the Laplace of the second derivative is s squared y of s minus sy of 0 minus y prime of 0. So those will be used when we start solving differential equations. To start with that, let's look at this example. We're going to solve dy dt, the differential equation dy dt minus 4y equals e to the 3t, with the given initial condition y of 0 equals 1. So to do that, we use linearity of the Laplace transform. We take Laplace for each term, like so, and then the Laplace of e to the 3t. So what do we get here? Remember, the Laplace of y of dy dt, it's over there. It's s capital Y of s minus y of 0 minus 4. Laplace of that is capital Y of s equals 1 over s minus 3. Then we can take these two together and factor capital Y of s. And we know y of 0 is given as 1, so minus 1 equals 1 over s minus 3. Remember, I want to solve for capital Y of s. So how do I do this? So keep this the same. Add 1 to both sides, so you get 1 over s minus 3 plus 1. And that can combine to s minus 2 over s minus 3. So I solved for y of s. Now we're going to simplify the right-hand side of that. Now we're going to solve for y of s by dividing both sides by s minus 4. So I get s minus 4. To find the inverse Laplace of that, we need to work on the right-hand side. So how do we work on the right-hand side? We use partial fraction decomposition. So this can be written as a over s minus 3 plus b over s minus 4. So then multiply everything by the least common denominator. So we get s minus 4 here and b times s minus 3. Not difficult to solve for a and b. We got a -1 and b to be 2. So then y of s can be written as a over, so -1 over s minus 3, b over, which is 2 over s minus 4. To finish solving for this, we do inverse Laplace of y of s equals -1 inverse Laplace of 1 over s minus 3 plus 2 inverse Laplace of 1 over s minus 4. So what does that give us? This is y of t that I'm looking for, negative. This is e to the 3t plus 2e to the 4t. That's the solution. So you could see how we use Laplace transformations to solve a differential equation. Let's look at another example. Let's say we're asked to solve y double prime minus 10y prime plus 25y equals t squared e to the 5t with the initial condition y of 0 is 3 and y prime of 0 is 15. So how do we start with this? Well, again, Laplace of each term by linearity of Laplace transform y prime plus 25 Laplace of y equals Laplace of t squared e to the 5t e to the 5t. Now, the Laplace of y double prime, we told you earlier, it's s squared capital Y of s minus s y of 0 minus y prime of 0 minus 10 bracket. The Laplace of y prime is s capital Y of s minus y of 0 plus 25 capital Y of S. Now, how do we find the Laplace of the right-hand side? I'm going to do that on the side. Just recall the Laplace of e to the at of f of t. We give it to you by the first translation theorem as capital of S of f of s minus a, which can also be written as the Laplace of f of t, where s can be replaced with s minus a. So for this thing that we have the Laplace of t squared e to the 5t, this can be found using the Laplace of the function f of t, which is t squared in this case, where s get replaced with s minus 5. And the Laplace of t squared is 2 factorial over s to the third, where s get replaced with s minus 5. 2 over s minus 5 to the third power. So that goes here, 2 over s minus 5 to the third power. So now we come back to this, nothing can be done here, minus y of 0. Y of 0 is given 3, so 3s minus y prime is given as 15 minus 10s y of s. Again, y of 0 is 3, that's a plus 3 times 10, 30, plus 25 y of s equals that term, 2 over s minus 5 to the third power. We are going to factor the terms involving y, capital Y of s, which is s squared minus 10s plus 25, capital Y of s, minus 3s plus 15 equals 2 over s minus 5 to the third. This can be factored as s minus 5 squared, capital Y of s. Move everything to the other side by subtraction and addition. Keep this the same for now. I can factor a 3 here, so that's s minus 5 plus 2 over s minus 5 to the third power. Now we can divide everything by s minus 5 to the fifth. So y of s is 3 over s minus 5 plus 2 over s minus 5 to the fifth power. If we do Laplace inverse for both sides, we get y of t equals 3 Laplace inverse of 1 over s minus 5 plus 2 Laplace inverse of 1 over s minus 5 to the fifth power. And then if we know for this one, what we need to do is, because I have s minus 5 to the fifth power, so the top should be times 4 factorial. We do the same thing here, 4 factorial. And we know on the left side, the inverse Laplace of 4 factorial of s to the fifth. What is this? This equal when s replaced with s minus 3. This is t to the fourth, e to the 3t. So what do we get for this one? This is 3. This is e to the 5t times 2 over 4 times plus 3, 4 times 3 times 2. And the Laplace inverse for that is t to the fourth, e to the 3t, the one that we just found on the right side. So the final answer would be 3e to the 5t plus 1 over 12 t to the fourth, e to the 3t. Another application here, that's how we solve differential equations using Laplace transform. So we have what we call Volterra integral equation. So we're going to see how to use Laplace to work this thing out. This is RR, 2 R's. So what do we do here? We use the convolution theorem. We use the convolution theorem to solve other kinds of equations, means differential equations, where the functions appear under the integral sign. So where we call them unknown functions. Unknown functions appear under an integral sign. So what do we have here? Well, f of t, the function we're trying to solve for, is f of t is g of t plus the integral from 0 to t f of tau times h of t minus tau d tau, where g of t and h of t are known. So g of t and h of t known. Okay, so also recall the one we wrote earlier, the Laplace of f convoluted with g is given the Laplace of f of t times the Laplace of g of t, and make sure that f convoluted with g is given by the integral 0 to t f of tau g of t minus tau d tau. We're going to be using that. So how do we use that up? Let's say we're asked to solve f of t equals 6t squared minus e negative t minus integral 0 to t f of tau e t minus tau d tau. And we need to solve this for f of t. That's what we're asked to do. So to do so, we take the Laplace both sides first. So the Laplace of, we take the 6 out, t squared, minus the Laplace of e negative t, minus the Laplace of integral 0 to t f of tau e to the t minus tau d tau. So let's see, on the left side we get capital F of s, that's the Laplace of f of t, equals 6 times, this one is 2 factorial over s cubed, this one is 1 over s minus minus 1 becomes plus 1, minus, this is the Laplace based on the recall one for the convolution, is f of t times the Laplace of g of t. In this case, g of t is e of t, e to the t. So if you convert this with this stuff, you can see it, g of t. So let's keep this the same. This is 12 over s cubed minus this stays the same. Minus, this is capital F of x. And this is 1 over s minus 1. And now what we need to do is solve for capital F of s. Because when we solve for capital F of s, at the end we do inverse Laplace, and that will give me small f of t. And that's what I'm looking for. So to do that, you can bring or collect the terms containing s of t on one side and the rest on the other side. So then you can factor s of capital F of s, 1 plus 1 over s minus 1, and let's keep this the same for now. Combining fractions inside the bracket, that gives us s over s minus 1, and let's keep this the same. So now we can divide both sides by, or multiply by s minus 1, so s minus 1 over s. So that would make it s minus 1 over s to the 4th minus s minus 1 times s plus 1, like so. So I multiplied the top of each fraction by s minus 1 and the denominator by s. That will clean the stuff on the left side. So now we can combine. There's many ways to finish this up. You can take the first fraction, split it up into 2 fractions, and then the last one you can do partial fraction decomposition for that. So if we break this out, that would be 12s over s cubed becomes 12 over s to the 4th. That becomes 12 over s cubed minus 12 over s to the 4th minus, we can do partial fraction decomposition on this and write it as a over s plus b over s plus 1 and multiply by the least common denominator. Solve for a and b. You should get negative 1 over s plus 2 over s plus 1. So at capital F of s is 12 over s cubed minus 12 over s to the 4th plus 1 over s minus 2 over s plus 1. So after we get all of this, now it's ready for inverse Laplace. So inverse Laplace of capital F of s equals 12 inverse Laplace of 1 over s cubed minus 12 inverse Laplace of 1 over s to the fourth plus inverse Laplace of 1 over s plus minus 2, last one, minus 2, inverse Laplace of 1 over s plus 1. So on the left hand side, this is very simple. It's f of t. That's what I'm looking for. That's what we're looking for. So for this one, we need to multiply this by 2 factorial, and we do the same thing in the denominator. For that one, we need to multiply by 3 factorial and do the same thing in the denominator. So we get 12 divided by 2 is 6, and the inverse Laplace of this one is t squared minus 3 factorial is 6. 12 divided by 6 is 2, and inverse Laplace of s to the fourth is t cubed plus inverse Laplace of 1 over s is just 1 minus 2e to the negative t. So that's the solution for that differential equation involving integral